Welcome. Today we are looking at energy changes at an advanced level. This is a key topic in your chemistry exams for SS3. Pay close attention. Let us begin. First, let me review what energy changes in chemical reactions are. All chemical reactions involve energy changes. Energy is either released or absorbed during a reaction. The energy change is usually in the form of heat. Reactions that release heat are called exothermic reactions. Reactions that absorb heat are called endothermic reactions. The study of energy changes in chemical reactions is called thermochemistry. Understanding energy changes is important for many reasons. It helps us understand why reactions occur. It helps us design industrial processes. It helps us understand biological systems. Energy changes are a fundamental part of chemistry. Now let me explain enthalpy in detail. Enthalpy is the heat content of a system. It is a measure of the total energy of a substance. The symbol for enthalpy is Ha. The change in enthalpy during a reaction is delta H. Delta H is the difference between the enthalpy of the products and the enthalpy of the reactants. If the products have less enthalpy than the reactants, delta H is negative. The reaction is exothermic. If the products have more enthalpy than the reactants, delta H is positive. The reaction is endothermic. Enthalpy is a state function. It depends only on the state of the system. It does not depend on the path taken. This is an important property. It allows us to calculate enthalpy changes using Hess's law. Now, let me explain standard enthalpy changes in detail. Standard enthalpy changes are measured under standard conditions. Standard conditions are 298 Kelvin and 1 atmosphere pressure. The standard enthalpy change of formation is the enthalpy change when 1 mole of a compound is formed from its elements in their standard states. The standard enthalpy change of combustion is the enthalpy change when 1 mole of a substance is burned completely in oxygen. The standard enthalpy change of neutralization is the enthalpy change when 1 mole of water is formed by the reaction of an acid and a base. The standard enthalpy change of solution is the enthalpy change when 1 mole of a solute dissolves in a solvent. The standard enthalpy change of atomization is the enthalpy change when 1 mole of gaseous atoms is formed from the element in its standard state. The standard enthalpy change of hydration is the enthalpy change when 1 mole of gaseous ions is hydrated. These standard values are used in calculations. Now let me explain Hess's law in detail. Hess's law states that the enthalpy change for a reaction is independent of the path taken. It depends only on the initial and final states. This means that the total enthalpy change for a reaction is the same whether the reaction occurs in one step or in several steps. Hess's law is used to calculate enthalpy changes that cannot be measured directly. For example, the enthalpy change for the formation of carbon monoxide cannot be measured directly. It can be calculated using Hess's law. Hess's law is a consequence of the fact that enthalpy is a state function. It is a powerful tool in thermochemistry. To use Hess's law, you write a series of reactions that add up to the target reaction. You add the enthalpy changes for each reaction. The sum is the enthalpy change for the target reaction. You may need to reverse reactions. Reversing a reaction changes the sign of delta H. You may need to multiply reactions by coefficients. Multiplying a reaction by a coefficient multiplies delta H by the same coefficient. Now let me explain bond energies in detail. Bond energy is the energy required to break 1 mole of a particular bond in a gaseous molecule. Bond breaking requires energy. It is endothermic. Bond making releases energy. It is exothermic. The enthalpy change of a reaction can be calculated using bond energies. The enthalpy change is the sum of the bond energies broken minus the sum of the bond energies formed. For example, the reaction H2 plus Cl2 equals 2HCl. The bond energy of HH is 436 kilojoules per mole. The bond energy of ClCl is 243 kilojoules per mole. The bond energy of HCl is 431 kilojoules per mole. The energy required to break bonds is 436 plus 243. This equals 679 kilojoules. The energy released when bonds are formed is 2 times 431. This equals 862 kilojoules. The enthalpy change is 670 minus 820. This equals negative 183 kilojoules. The reaction is exothermic. Bond energies are average values. They are not exact for every molecule, but they are useful for approximate calculations. Now let me explain enthalpy of formation and its applications. The enthalpy of formation is the enthalpy change when 1 mole of a compound is formed from its elements in their standard states. The standard enthalpy of formation of an element in its standard state is 0. The enthalpy of formation can be used to calculate the enthalpy change of a reaction. The enthalpy change of a reaction is the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants. For example, the enthalpy change for the reaction CH4 plus 2O2 equals CO2 plus 2H2O can be calculated. The enthalpy of formation of Trier is negative 74, 8 kilojoule per mole. The enthalpy of formation of O2 is 0. The enthalpy of formation of CO2 is negative 393.5 kilojoules per mole. The enthalpy of formation of HCl is negative 285, 8 kilojoule per mole. The enthalpy change is 399.5 plus 2 times 258 minus 44.8 plus 0. This equals negative 965.1 minus negative 74.8. The result is negative 890. 3 kilojoule. The reaction is exothermic. The enthalpy of formation method is very useful for calculating enthalpy changes. Now, let me explain entropy. Entropy is a measure of disorder or randomness. The symbol for entropy is S. The change in entropy is delta S. A positive delta S means an increase in disorder. A negative delta S means a decrease in disorder. Entropy increases when a solid melts to a liquid. It increases when a liquid boils to a gas. It increases when the number of moles of gas increases. The entropy of a system is related to the number of possible arrangements of its particles. The second law of thermodynamics states that the entropy of the universe increases for a spontaneous process. The entropy change of the universe is the sum of the entropy change of the system and the entropy change of the surroundings. A spontaneous process must have a positive entropy change for the universe. Now let me explain Gibbs free energy. Gibbs free energy is a thermodynamic quantity that combines enthalpy and entropy. It is used to predict whether a reaction is spontaneous. The symbol for Gibbs free energy is G. The change in Gibbs free energy is delta G. The relationship is delta G equals delta H minus T times delta S. T is the temperature in Kelvin. If delta G is negative, the reaction is spontaneous. If delta G is positive, the reaction is not spontaneous. If delta G is 0, the reaction is at equilibrium. Gibbs free energy is a state function. It depends only on the initial and final states. It does not depend on the path taken. Gibbs free energy is very useful for predicting the feasibility of reactions. A reaction can be spontaneous even if it is endothermic. If the entropy increase is large enough, delta G can be negative. Now, let me explain the relationship between delta G and equilibrium. The standard Gibbs free energy change is related to the equilibrium constant. The relationship is delta G standard equals RT ln K. R is the gas constant. T is the temperature. K is the equilibrium constant. If K is large, delta G standard is negative. The products are favored. If K is small, delta G standard is positive. The reactants are favored. If K is 1, delta G standard is 0. the reaction is at equilibrium. This relationship is very useful. It allows us to calculate the equilibrium constant from thermodynamic data. It also allows us to predict the direction of a reaction. A common exam question asks you to calculate enthalpy change using bond energies. Here is a sample answer. Enthalpy change equals sum of bond energies broken minus sum of bond energies formed. Bond breaking requires energy. It is endothermic. Bond making releases energy. It is exothermic. The enthalpy change is positive for endothermic reactions and negative for exothermic reactions. Bond energies are average values. They are useful for approximate calculations. Another exam question asks you to use Hess's law to calculate an enthalpy change. Here is your answer. Hess's law states that the enthalpy change for a reaction is independent of the path. To calculate an enthalpy change, write a series of reactions that add up to the target reaction. Reverse reactions if necessary. Multiply reactions by coefficients as needed. Add the enthalpy changes. The sum is the enthalpy change for the target reaction. Hess's law is based on the fact that enthalpy is a state function. Another exam question asks you to explain Gibbs free energy. Here is your answer. Gibbs free energy is a thermodynamic quantity that combines enthalpy and entropy. It is used to predict whether a reaction is spontaneous. Delta G equals delta H minus T times delta S. If delta G is negative, the reaction is spontaneous. If delta G is positive, the reaction is not spontaneous. If delta G is 0, the reaction is at equilibrium. Gibbs free energy is very useful for predicting the feasibility of reactions. Let me give you a quick summary. Enthalpy is the heat content of a system. Hess's law allows calculation of enthalpy changes. Bond energies can be used to calculate enthalpy changes. Entropy is a measure of disorder. Gibbs free energy combines enthalpy and entropy. It predicts spontaneity. Delta G equals delta H minus T times delta S. Delta G is related to the equilibrium constant. Practice these concepts. When you have them down, move to topic 6.